Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the 21st lecture. In this lecture, we will be looking at technology library. In the earlier lectures, we had looked into logic synthesis and we have seen that how the transformation of an RTL to netlist consisting of generic logic gates is done. And we had also looked into logic optimization that is performed on netlist consisting of generic logic gates. Subsequently, in the design flow, we want to map these generic logic gates into the cells of the given technology library, and we also want to do various analysis and various verification steps we want to carry out on our design. For example, we want to do timing analysis and power analysis and so on. Now, the generic logic gates does not contain the attributes of the cell such as timing, power and so on. However, the cells of a technology library contains those attributes, and those attributes are inside the technology library, and therefore, we need to or the tool needs to look into the technology library to convert a netlist that is consisting of generic logic gates to the cells of the given technology library. So, the information contained in technology library is very important for the subsequent design flows, not only for the implementation but also for the verification. So, in this lecture we will be looking into the details of or some details of the technology library. Now, the libraries that we use in VLSI design flow are of two types. The first one is the technology library and the second one is the physical library. So, these are the most commonly used libraries in our design flows. Now, what are differences between these two libraries? So, let us first understand that. So, the technology library was initially created basically for the logic synthesis purpose, and initially it contained only say of the details such as functionality of a logic cell or a cell. For example, it says that okay, this is an AND gate, this is an OR gate, and those kind of functionality were specified for the standard cells in the technology library. But with time what happened is that this technology library evolved, and it started supporting or it started containing many useful information for the design flow. For example, it contains information for timing verification, for physical implementation and also for carrying out test activities, which we will see later in this course. So, technology library contains a lot of information for which are useful throughout the VLSI design flow. And since these technology libraries contain primarily the data or the information of timing, therefore, sometimes we also call these technology libraries as timing library, but keep in mind that technology library also contains information of power and many other information that we will see subsequently in this lecture. So, in which format do we specify this technology libraries? So, the most common way in which these technology libraries or the informations of the cells in a technology is encapsulated is in the liberty format. Okay. So, the format in which the technology library is typically used in the design flow, that format is known as the liberty format, and the technology libraries typically have got the extension of .lib. So, if you have a design infrastructure, in that infrastructure if you have say that .lib files, then this .lib files most likely contains information of the technology library. And these are ASCII files, meaning that you can open it in an editor and just see that what characters and what things are written there, right. So, these technology libraries are human readable. Now, what about the physical libraries? So, physical library contains abstract information about the layout of the cells and the technology, for example, the resistance per square and capacitance and so on. So, it contains information of the technology, such as say how many layers are there in the technology, and also it contains the information in some abstract form about the layout of a cell, that where the pins are and so on. So, these informations are there in physical library, and the physical library is typically specified in a format which is known as library exchange format or LEF format, LEF format. And typically these the files, the LEF files will have an extension .LEF, right. The extension will be .LEF, and these are also human readable or ASCII files, right. Now, these physical libraries are used in the physical design process, and we will be looking into physical libraries in detail later in our course when we discuss physical design task. So, in today's lecture we will be concentrating or focusing on the technology library. Now, what is the motivation for using technology library? Why do we use technology library in our design flow? So, the primary motivation is to simplify the design task, right. So, the design task is basically finally getting a layout of or a layout which delivers the required functionality, right. Now, this is a very complicated task, and therefore, we need to simplify it, and we divide this design task into two tasks, and therefore, we are trying to simplify it or make it a two-step process. And there are many benefits of having this two-step process. And what are these two steps? So, the first step is creating library. So, the first step in designing is creating the library, and the second step is using the library. Now, what we mean by creating library, what we mean by using library, we will just see. So, creating library means that we are designing cells, we are designing standard cells at the transistor level, right. So, we are designing cells in a most optimum way, for example, a NAND gate, AND gate, inverter, and such cells are designed at the transistor level, meaning that we make the topology, we make the layout of the cells, do spice simulation, verify the functionality, and if we can make some improvement in the layout, we do those things and make our cells very optimal in terms of what it delivers the functionality, and also in terms of figure of merit, meaning the delay and the power and the area and so on. So, the first step is while creating library is that we design cells at the transistor level, right. So, if we determine its optimal layout for each of the cell, for example, there will be AND gate, OR gate, NAND, NOR, flip flops and so on. Many types of cells will be there, and we will be designing or making an optimal layout for all these individual cells. That is done, what is done in the creating library step. And then after we have designed our cells, we extract useful information out of those cells and keep them in a format, or write them in a format of .lib or liberty format or some other format. Is we keep the information of the individual cells, and that once we keep that information of that in some file or in some repository, then that constitutes a library, and then we have created a library. Okay. So, now once we have created this library, then this library can be used by multiple designs. For example, using the same library, say we have created a library for 45 nanometer technology, then using this library, many designs can be taped out, or the layout of that can be designed, and then fabricate it. For example, we can get a processor, different types of processors, we can get a security chip, or we can get various other functionality or chips of different functionality using the standard cells of the same library. So, once we have designed many cells and a rich set of library or consisting of many cells, we extract information and put those information in some form of library, then that library can be used multiple times in various for various designs and for creating many chips. Now, how does it help? So, it helps by reducing the cost. So, the cost of developing a high quality library gets distributed over multiple designs. For example, if we create one library and the same library is used by say 100 designs, right. For example, the various processors or various kind of controllers and many other chips that we have made using the same library, say hundreds of designs are based on the same library. Then the cost in developing that library is distributed over all the 100 designs, right. So, the overall cost of developing a high quality library and highly optimized standard cells, though that get distributed or gets amortized over multiple designs, right. So, that is why it saves cost. Okay. So, this one, the creating library is the first part. The second part is using library in our designs, right. So, we said that using the one library 100 designs were made, right, separate designs were made. Now, these designs are using the library. So, in using library, what a designer need to do? The designer need to instantiate cells from the library to achieve the desired functionality. Suppose there were say 1000 cells in a library. Now, these standard cells will be picked by the designer and instantiated in the layout, and a design will be created. So, the focus of using library is instantiation rather than designing individual cells. So, it allows designer to focus just on the instantiations of the cells rather than going into the details of the standard cells, and therefore, the design time and the effort of the designer who is using this library, that decreases. So, and it also reduces the chances of introducing bugs inside the cells, right. So, once the cell is created in a library, we do not change the internal structure or internal details of the cell, right. And if we are not changing, we cannot make errors, right. So, the person who is using the library cannot introduce any extra errors inside the cells, right, because he or she is not making any change inside the library cells. The changes are only in the instantiations, right. So, the scope of error that also decreases a lot in creating a say multi-million gate design. So, and it raises the abstraction levels of the tools that are used in the design flows. So, raises the abstraction level from the transistor to the cell level, right. So, what it means is that say suppose a tool is doing timing analysis. Now, the timing analysis need not be done on a design at the transistor level, but the tool can do the analysis at the cell level and using a higher level of abstraction, right. So, the design tools that will be used in using the library, those design tools need to work at the higher level of abstraction, and that higher level of abstraction is the cell level instead of a lower level abstraction, that is a transistor level. By raising the level of abstraction, what happens is that the tool the tasks for these tools that decreases, or the complexity of the task decreases tremendously. For example, for the STA tool, for the physical design tools and the synthesis tools, the tasks become much easier if they are working at a higher level of abstraction. So, these are the primary motivation of making the design flow into two parts. The first part is creating the library, and the second part is using the library. Now, let us understand that how a library is created. Okay. So, library is created using a process which is known as library characterization, and this library characterization can be done either at the foundry level, who is developing the technology. The foundry can also develop a library. They can design the standard cells and then give the library to the designer, and the designer will do the will basically instantiate those cells in the libraries and make a design, right. So, either this characterization can be done at the foundry, in which the foundry creates the library, or a design house, individual design house can also undertake creating the libraries on their own, right. Now, let us look into the various tasks that are done during creation of a library. So, in the library creation, what is done? The first part is we need to design each cell optimally and verify that the functionality of the cell is correct. For example, AND gate is working as an AND gate, right, and we have to or design the cell optimally, meaning that the area should be low, the timing should be as good as possible, and the trade off should be a good trade off should be there between the timing and the area, and the power numbers should also be acceptable, and those kind of things are considered during designing the cell. Okay. So, once we have got the designed cell, then what is done is that we do spice simulations. We do spice simulations for these cells, and while doing this spice simulation, we specify various operating conditions and various stimulus. For example, given as an AND gate, what will be the stimulus at one input and what will be the stimulus at the other input, and so on. So, the stimulus and the operating conditions are decided, and then the information of the transistor. Now, this spice simulation is done at the transistor level. Okay. It is done at the transistor level, and during this simulation, it needs information about the transistor, the process, and so on. So, that information is contained in the PDK or process design kit, right, that we had seen earlier in the lectures. So, using this PDKs and the layout of the cell that we have designed and the given stimulus, spice simulation will be done, and based on the spice simulation, we measure and extract the parameters of interest. For example, what is the delay under a given stimulus, right, and then what would be the slew, what will be the transition at the output, right, or what will be the voltage swing, what will be the capacitance. So, these kind of information is extracted from the spice simulator, right, while doing spice simulation, and once this information is gathered, then this an abstract model is built and written in a given format, and which can be, say, the Liberty format, right. So, from the measured and extracted physical and electrical quantities, an abstract model is built, meaning that a model which can be used later on by various synthesis and various design tools such as synthesis, STA or static timing analysis, and physical design tools, and so on. So, abstract model is built, and that model is then written in a file which will be .lib file or is in the Liberty format. And then once we get this library files, then this will be used in the design flows subsequently. Now, why are spice simulations using PDKs not directly used in power delay computation? So, let us understand that what will happen if we directly use the spice simulation in our design flow, right. We are saying that in the design flow, or when we are using the library, the design tools work at a higher level of abstraction. They work at the cell level rather than at the transistor level. Now, what if those tools were working at the transistor level? They were doing spice simulations using PDKs, then what will happen, right. So, in that case, the tools will take a lot of time, right, because spice simulations are time taking, and they are time taking because these spice simulations are very accurate, right? They build differential equations given for a given circuit, and then those differential equations are solved iteratively using iterative technique, and these spice simulations are time taking, right? Now, for each instances in our design we try to do this kind of spice simulation, then it will lead to it will lead to a huge runtime, and that will not be acceptable. So, what is done is that therefore, we use library models in our design flows, right. So, what we do is that we extract information of that we gathered for individual cells during spice simulation and model in the library, as we have seen in the library characterization step, right. So, the EDA tools use library models instead of spice simulation for computing delay, slew, power, voltage variations, etc. And these are orders of magnitude, maybe 100 or 1000 times faster than what would be the runtime if we directly use spice simulations, right. So, this is the primary motivation of using library models in our design flow. It speeds up, right. Now, it speeds up our all the verification and the implementation task, right. Now, to allow this to be done seamlessly, we have to consider some important attributes that these library models should have. And what are these attributes? So, the first attribute is regarding the speed and accuracy trade-off. So, now we are creating an abstract model, right. So, we are using some abstract model, or we extract information and model in the library. So, we are not modeling everything that we get from the spice simulation in our library. We model only important things that we consider will be required in computing, say, delay and other things, right. So, we are actually losing some information from spice simulation, but the trick is that we should lose that information which is redundant, meaning that the accuracy loss by removing some information should be acceptable compared to the spice simulation, which is considered as the golden result. Then the second important attribute of a library model is the robustness. So, what we mean by robustness is that suppose there was an inverter in our library. Now, that inverter will be used at say 100 different places in our design, in our layout. So, the number of instances of an inverter can be very huge, and what we want is that for each instance of the inverter, the result should be, or the delay number or power number should be computed accurately in comparison to the spice simulation, right. So, the accuracy of the model should not be dependent on the instantiation or the environment in which we put our standard cells, right. So, the library models for these standard cells should be such that these models work fairly accurately at all kinds of instances in our design, right. That is what is meant by robustness, and in our library model should be robust enough to handle various instantiation scenario. And then this library model should be portable. It should not be that this library model is usable only in this tool. It should be usable in, say, static timing analysis, it should be usable in, say, synthesis, physical design and so on, and not only in various stages of design flow, it should also be portable from one vendor to another, right. So, we use the EDA tools from various vendors. So, an ideal library model should be one which works with all vendors of all EDA vendors or the tools of EDA vendors, right. And then the library models or library should have variety of cells, and there should also be some uniformity. What we mean by variety and uniformity, let us see. So, by variety we means that we should have multiple cells of the same function. For example, if we have, say, an inverter, so we should have inverter of, say, size 1x, size 2x, size 4x, and so on, right. So, as we increase the size of the inverter, then the drive strength will increase, right, and as a result it will become, say, a faster, it can drive the load faster, but at the same time it will incur more area on the wafer, right. So, now the library should be rich enough and it should contain instances, or sorry, cells of various drive strength and the same functionality. Why we want to do this? We want to do this so that there is sufficient degree of freedom for the synthesis and physical design tools, right. So, if there is a critical path, then probably the tool can instantiate, the synthesis tool can instantiate, say, inverter of size 4, right, then it will be driving much faster than the case for for an inverter of drive strength, say 1x, right, or 4 times smaller than 4x, right. So, and if an instance is not in a critical path, then probably it can use the inverter of size 1x, right. So, we give the freedom to the synthesis and implementation tool to choose whichever library cell it wants to pick based on the trade-offs of various figures of merit, right. And that is why we want the library to be as rich as possible, right. So, then it will have the tool will have many choices for various instances, and it will pick the right choice based on its requirement. And then there are we want libraries of various flavors, meaning that some library will deliver low power, some library will deliver high performance, some library will be very compact, have very compact cell and will give high density, or there can be libraries of different threshold voltage, which we call as low VT library, or low threshold voltage transistor, and then there can be high threshold voltage transistors and so on. So, depending on our design requirement, we can use different libraries for the same technology. And what about the uniformity? So, now we have created various types of or for the same functionality, for example, inverter, we created in this case 3 different sizes of inverters, right. Now, while creating these these cells, we also maintain some uniformity, and the most commonly used uniformity is uniformity in height, meaning that though the size of the cell will change, for example, 4x will be 4 times bigger than the the inverter of 1x size, but we do not change the height of the cell, we keep it fixed, right. We keep the, so what do we change? We change the width. For example, if this is the layout for the 1x inverter of size 1x, then the size of, or the layout of 4x inverter will be something like this. The height will remain the same, the width will be increased by 4 times, right. So, why do we put this kind of constraint on the height of the cell? We do this so that the physical design tasks become very easy, right. So, if we keep the height of the standard cell uniform, then we can arrange standard cell in a kind of height, in various rows of a constant height and so on, and that makes making layout and do routing much easier than if the height was allowed to be changed in arbitrary manner. So, it eases the task of physical design. Now, what does a library contain? Now, let us go into the library and understand that what things are there in the library. So, it contains information of process parameters, voltage and temperatures, and these three parameters are basically clubbed together, and we call them as PVT. Okay. So, PVT condition, right. So, we encounter this term PVT many times in design flow. And what PVT refer to? PVT refer to process, voltage and temperature, combination of these three things. And this information is there in the library, right. Now, and library contains many cells, and therefore it contains cell data, and in cells we have various pins, right, and then pins will have functionality, and other information of timing, area and power for the cells will also be there at the cell level. And then what type of cells are there in the library? So, library typically contains cells of hundreds of different logic functions. For example, there will be combinational and sequential standard cells, for example, AND gate, OR gate and so on, flip flops, latches, and these types of gates will be there in the libraries. Then there will be IO pads, those are special kind of cells through which signals come inside our chip, those are known as IO pads or input output pads. And there can be also more, cells which are implementing memory functions, and there can be bigger macros also, for example, half adder or adders, multiplies and those things, those information can also be or the cells of these type can also be there in the technology library. Now, when do we use libraries? So, we use libraries throughout our design flow from RTL to GDS. So, and it is used in synthesis, timing and power analysis, verification, design for test, physical design. So, in rest of the lectures that we will be discussing, most of them will actually be using some information from the library, and therefore, we have started looking into library before we move to the other design task. Now, what is the format in which we keep the information in the library? So, the format is Liberty format, and as we discussed, it is an ASCII or text format. Now, in Liberty format, so in the data is primarily stored as attributes. Okay, so in Liberty format, how is data stored? As attributes, and so there is a mapping between an attribute name and the value. So, there will be a name and value, right. For example, there will be an attribute name which is time unit and its value is say 10 picosecond, right. So, this is a name value pair, attribute name is time unit and the value is 10 picosecond. Now, in library the information is organized as hierarchy of groups. So, let us see what is this hierarchy of groups. So, this is the structure of a of information in a Liberty format. At the top there is a header, right, and what does header consist of, right, what does the header contain. So, at the top level there is a header, and header contains PVT information, scaling factors, units. It contains information that are valid for all the cells and pin and arcs in our inside the library, and then it contains the list of cells. So, these are list of cells. So, we have header and then we have list of cells. Now, what does a cell contain? Now, cell contains the information which is relevant for the cell, for example, its area, the leakage power at the cell level, and then it will contain list of pins. A cell will contain the list of pins, right. Now, what does a pin contain? Now, pin contain the information which is relevant for the pin level, for example, what its direction, what is its name, what is capacitance, then what is its functionality, meaning whether it is an AND gate, OR gate and so on, those functionality is specified at the pin level, and then it contains the list of timing arcs and also list of power arcs. So, this is how the information is organized in a technology library. Now, timing arcs are used to perform timing analysis and computing delays of the arcs, and power arcs are used to perform power analysis. So, we will be looking into timing arcs in more detail in this lecture. Okay. Now, what are timing arcs? So, timing arcs are used to model timing attributes for combinational and sequential cells in the library. For example, consider this cell, this cell may be say inverter, an AND gate, OR gate or whatever, right. So, for this cell there is a pin A and there is a pin Z, right. For example, if we consider it as inverter, then there is a pin A, there is a pin Z, right. Now, we know that there is a delay arc or there is a delay between the input A and Z, right. So, that information will be modeled using timing arc. Now, more formally, what does a timing arc has? Timing arc has a start pin, in this case A, right, and an end pin, in this case Z, right. So, the timing arc is specified at the end pin, meaning that at the pin Z. So, this is a snippet of a technology library. So, there will be a pin Z specified, and inside this pin Z there is the information about the timing arc, right. Now, so timing arc is specified. So, this timing arc, the information about this timing arc will be specified at the end pin, right. So, end pin in this case is Z. So, it will be specified at the pin Z, right, and the start pin is specified using the attribute related pin. So, inside this timing arc we have an attribute called related pin whose value is A. So, what does this A signify? This A signifies the start pin, right. So, this is how the timing arcs exist in our technology library. Now, the timing arcs can be of two types. The first one is delay arc and the second type is of constraint arc. So, constraint arc are related to setup check and hold check. So, we will be looking into these both types of arc in more detail. Now, what does this timing arc contain? So, this timing arc contains attributes of timing for a given arc. And what are these attributes? So, these attributes can be related to slew or it can be related to say delay, right. So, what is slew? Let us understand that first. So, slew of a signal quantifies how steeply or sharply transition occurs from 0 to 1 or 1 to 0, meaning that you have 0 and you have 1, right. So, how steeply it goes, right, how fast it goes from 0 to 1 or 1 to 0, that is measured by the slew of a signal. Okay. So, slew is measured by defining two transition points. Now, in technology library we define slew by assuming that our signal is rising in a linear manner, right. So, if say it is a 0, this is a 1, we say that from 0 to 1 the signal rises in some manner and the slew characterizes basically then average kind of slope of this line, right. Now, to measure this slope, what is done during characterization of a timing library? First, two transition points are chosen. These transition points are known as lower threshold percentage LTP and upper threshold percentage or UTP, and this information is present in the header of the technology library. So, what are these two transition points? For example, the library during library characterization we can say that lower threshold percentage is say 10% and these are with respect to the VDD of the signal. So, the one point is the 10% of the VDD, this point it may be, and the upper threshold point can be this point, which can be say 90%, right. So, we say that there is a signal and we have chosen during library characterization say at 10% as LTP and 90% as UTP. Then this kind of threshold is known as 10-90 threshold because we have to take in 2 points 10% and 90%, right. So, based on this definition or this choice of our threshold point or transition point, how do we define slew? So, we define that the slew can be different for the rising and the falling case. So, in this case since the signal is rising, we say that this is a right slew and this is the time taken for a signal to reach from 10% to 90%. So, whatever is the time duration of 10% to 90% 90%, 90% to 100%, 100% to 90%, 100% to 100%, 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 100% to 100 or time taken for a signal to go from 10% to 90%, that is defined as a slew of the signal, right. So, similarly we can define fall slew as the time taken by the signal to go from say UTP to LTP, right. So, in this case it is 90% to 10%, right. Similarly, the slew threshold can be between 20 to 80, right. So, LTP can be chosen as 20, UTP can be chosen as 80. So, then it is known as 20-80 threshold, or it can be 30-70 threshold. So, whatever the threshold will be, that will be predefined in the header of the technology file, and from there we can get the information, or the tool can get the information that what was the definition of slew used by the tool while characterizing, right. Now, these slew, rise slew, fall slew are also known as rise transition time, fall transition time, rise time and fall time also, right. So, there are various names, all refer to the same thing, meaning how sharp the transition occurs from 0 to 1 or 1 to 0. Now, the other definition is related to the delay of the timing arcs. Now, what does delay quantifies? It quantifies how much time it takes for the change in input to propagate to the output, and therefore, this is a delay is also known as propagation delay, right. So, suppose we had a timing arc from this source to the destination, right. So, the delay can depend on the direction of the transition, meaning that whether the transition is at the output is rising or it is falling, right. The delay can be different, right. For the rise transition or the fall transition, the delay can be different, and therefore, we define two types of delays. One is the rise delay, and rise delay is the delay which is refers to the delay observed when output is rising, right. So, note that the rise delay is with respect to the how the signal is transitioning at the output, not at the input, right. So, rise delay is output rising and fall delay is output falling. So, the convention is that we define a delay arc based on the transition at the output of the arc, not at the input of the arc, that is the convention. Okay. Then again, as we had chosen threshold for the slew, similarly we choose threshold for the delay also for characterizing. So, during characterization, a predefined threshold points on the input waveform and the output waveform are chosen. So, separate thresholds are there for the input and the output, and these thresholds are mentioned in the header of the technology lab. Now, the input signal can be either rising or falling. So, for the case when the input signal is rising, we define input rise threshold percentage IRTP and input, and for the falling case input fall threshold percentage IFTP. So, these threshold points are mentioned in the technology library. For example, let us consider this input signal, right. So, we had this was the input signal, and corresponding to this input signal the output was this signal, right. Now, at the input side we have defined a threshold as 50%, right. So, we have chosen an IRTP as 50%, right. Since it is a rising input is rising, so we have to take the input rise threshold percentage or IRTP. Suppose it was 50%. So, this point refers to the IRTP point, right. Similarly, for the output signal we define output rise threshold percentage and output fall threshold percentage. Now, this is the output signal, right, and we define, suppose we have defined output rise fall threshold percentage as 50%. Now, since this signal is rising, we have to use this threshold, right. So, now how do we define delay? Now, we define delay as the time elapsed between the input crossing the input threshold point and the output crossing the output threshold point, right. So, the difference between this, the delay between this, or the time elapsed or time interval between these 2 points, this is defined as the delay. So, in this case the output is rising, so this is a rise delay, right. Similarly, if we consider that the input was rising and the output was falling, so since the input was rising, we have to take IRTP as the threshold point, this one, right, and since the output is falling, so we have to take this one, right. Assume that this one was also specified as 50% in the technology library. So, we get the 50% point or 50% of VDD point this, and the time elapsed between these two, this is known as the fall delay. Why fall delay? Because output is falling, right. So, this is how we define delay in our technology library. Now, let us look at how does the delay and the slew of a gate is characterized in the technology library. Now, let us consider this NAND gate, which drives a load of value CL. This is a capacitive load, and it gets a signal which is rising, and it has got a slew of Si, right. Now, if we consider the delay of this timing arc and its output slew, meaning the slew at this output pin Z, then these two things, delay and output slew, depends on the input slew, that how fast the signal is transitioning at the input, and the load, the capacitive load that is there at the output, right. So, the delay and the output slew depends on the input slew and the capacitive load, right. So, the delay and slew depends on these two things, right. So, if we look into this relationship between these delay and this input slew and output load, we will find that delay and output slew is a non-linear function. Now, this is a monotonic a non-linear relationship, and modeling this in capturing this information in the technology library is a bit difficult. So, how do we handle this case? So, we model the delay and the output slew as two-dimensional discrete point tables, right. So, we model them as two-dimensional discrete point tables like this. So, we choose a set of capacitive load, right, CL1, CL2 and CLN. We have chosen n capacitive load, and we choose say m input slew Si1, Si2 and Sim. So, these are the input slew. Now, for each discrete slew and capacitive load, we will have a separate delay and the output slew value, right. So, this is how we approximately model this nonlinear relationship of delay and output slew on the input slew and the output load, right. And if we are in the design we get say load which is something between CL2 and CL3, right. So, and we get a input slew which is something between Si2 and Si3. So, we will choose these 4 values, right, corresponding to these numbers, and use some technique of interpolation, maybe linear interpolation or so on, to compute the delay and the output slew, right. So, this is how the information is modeled inside the library. It is modeled as discrete two-dimensional table, and this model is known as NLDM, non-linear delay model. Now, we will have different tables for delay and output slew. Now, let us look at how is this the delay model or non-linear delay model written in the technology library. Suppose we had a timing arc between A and Z, right. Now, corresponding to this arc, we will have a timing arc something like this, right. So, at the header there will be say 2 variables, one corresponding to slew and other corresponding to load, and then we have the index 1 and index 2, which is showing that slew is varying or taking values of 10, 12, 30 and 10, 20, 30, and load is taking a value of 1.2, 5.0, 15.0 and 37.5, right. Now, corresponding to this slew and load, there is a rise delay, right, on the timing arc between Z and A, right, this timing arc, because related pin is A, right. So, and there is a cell rise attribute which says that it is a rise delay, right, at the output, right, and we have a table which specifies that there are for different combination of slew and load, we have different values, right. So, since there are three slews numbers and 4 load numbers, there are 3 into 4 is equal to 12 entries in this in this timing arc. Now, the modeling of delay and slew that is done using the NLDM model is not always accurate, especially at the advanced process nodes. There is a significant accuracy loss, and there are many reasons for that. So, one of them is that in NLDM model, we are assuming that the output is or a cell drives an output which is totally capacitive, right. Now, what if there is a high resistance at the output, right. So, in that case and also because of say Miller effects and also due to non-linear effects, the assumption of the slew being one number, that becomes inaccurate. What I mean to say is that suppose there was a non-linear signal, right, there was a non-linear signal. Now, for a non-linear signal, assuming that the signal has got one slope and that can be represented using slew, that is may not be accurate, and there are accuracy losses because of that. Therefore, at advanced process node, what we do is that we use other delay models, for example, based on current source models. So, at advanced process nodes, we use two types of current source model. The first one is known as composite current source model or CCS, and the second one is effective current source model or ECSM. So, these current models, these delay models are more accurate than the NLDM model, and at advanced process nodes we use these type of models. Now, let us look into another type of attribute which is important for the cells or especially for the sequential cells in our design, and these are related to the setup time and hold time. Now, before going into the modeling of setup and hold time, let us understand what is a setup time and hold time. Now, suppose there is a flip flop. So, for a flip flop to work deterministically, a kind of relationship should be satisfied between data and the clock signal, meaning that whenever the clock is say rising, the data should not change within some window of that, right. So, there is some kind of forbidden timing window around the clock edge where we do not allow the data to change, right. So, we define a forbidden window around the clock signal. Suppose this was the clock signal, right. So, we have a clock signal which is rising, and this is say data signal. Now, if there is a data signal changes very close to this clock edge, then the data that will be captured by the flip flop, that cannot be reliably said to be 1 or 0. It can be something which we do not know, and that state is known as kind of metastable state, and we try to avoid that situation where we do not know what is the state of a flip flop, right. So, what we define this window around this clock edge by two attributes, and these attributes are known as setup time and hold time of the flip flop. Now, what is a setup time? So, setup time is the minimum amount of time the data signal should be held steady before the clock edge, right. So, if this is the clock edge, before this clock edge, we say that the data signal should get stabilized within this window. It should not change below this or before this clock edge for some time, and what is that time? That time is known as the setup time. So, before the clock edge, the data should not change for the setup time duration, right. In this window, we are not allowing this data to change. If data changes within this window, the value at the output pin Q of the flip flop cannot be deterministically set to be 0 or 1, right. So, we do not, this is a forbidden window for change on the or before the clock edge. And similarly, we define that the minimum amount of time the data signal should be held steady after the clock edge, so that data is sampled correctly and deterministically. So, after the clock edge, we do not allow the data to change within for some window, right, and that window is till this time. Within this time, we do not allow the data to change. If data changes within this small period after the clock edge, that is defined by the clock hold time, that then we say that then the output Q may take any value or non, we cannot deterministically say whether it is 0 or 1. So, we define hold time as that minimum amount of time the data signal should be held steady after the clock edge, so that data is sampled correctly and deterministically. Now, these setup and hold times are modeled inside our inside our library. Why do we want to model this inside our library? Because these are attributes of the standard shells, for example, the flip flops, right, and these can be measured, setup and hold time can be measured only with the help of say SPICE simulations. So, only one who is doing the library characterization, they can know that what are the constraints imposed on or that should be imposed on the flip flop, so that the data is captured reliably, right. So, that is why we need to model setup and hold time in our library itself. So, in general, the setup and hold time constraint depends on the data slew, meaning that how fast the data signal is changing, right, from 0 to 1 or 1 to 0, and the clock slew, the how fast or how steeply the data is going from 0 or signal is going from 0 to 1 at the clock side. So, the setup and hold time depends on the slew at the data and the slew at the clock, right. Now, in general, again it is a non-linear function, and similar to NLDM, we can model it as two-dimensional discrete point tables, and we keep, there are different tables for setup and hold, right. So, similar to NLDM, what we do is that in this case also we have a two-dimensional table consisting of two variables, two input variables, and these two input variables are data slew and the clock slew, right. And what are the output variables? The output variables are the setup time and the hold time. So, let us take an example of a library, and then we can understand. Suppose this was our cell, right, this was a flip flop, right. Now, corresponding to this, there will be a technology, the technology library can model the setup time in the way that is shown in this figure. So, we will have constrained pin transition and we will have related pin transition, right. So, there are two types of transition, one is related pin time transition, other is constrained pin transition, referring to the transition at the data pin and the clock pin, right. And then the setup time is specified on the pin D, right, the data pin, and the related pin is the clock pin, right. So, the related pin is the clock pin, and that is why there is a arc, right, between between these two. And then we will, since there are 3 values for constrained pin and 4 values for related pin, there will be a 3 cross 4 table for the rise constraint for the setup case. Similarly, there will be another table for hold, for hold case, hold time, right. So, similar to what we have rise constraint, there can be a fall constraint corresponding to data falling, right. So, this is how the setup time and hold times are modeled inside the library. Now, if the slew at the data signal and the clock signal take some intermediate values, right, then which is not modeled according to the selected points, then some interpolation technique will be used, as we have seen for the delay case, right. Now, these are some, what we saw are some of the information or some of the important information that are modeled inside a technology library, right. In addition to this, there are lots of other information which are contained in technology library. So, the other information is related to power. So, when we will be discussing power analysis, then we will be looking into power models more carefully. Then there are models for crosstalk and SI analysis and noise analysis, right. And there are information of power ground pins for the standard cells or the cells in our library. And then there are some arcs which are conditional arcs, meaning that those arcs get active only when some condition holds at the other inputs, right. So, those are known as conditional arcs, and those are defined by SDF con and when conditions. And then there are some attributes, so other attributes which will be there in the library, which can be very much vendor specific, right. So, in addition to the attributes which are supported natively by Liberty, right, there are other attributes which can be vendor specific, and there are ways in which we can extend the syntax to include vendor specific information in our technology library, right. So, if you want to go deeper into the concepts that we discussed in this lecture, you can refer to these materials. So, to summarize, in this lecture we have looked into technology library, we have looked into the motivation of using technology library in design flows, we looked into the characterization and the format in which technology library is represented. We also looked into nonlinear delay model and how setup and hold time of flip flops are modeled. From next lecture onward, we will be looking into timing analysis or static timing analysis, which is one of the most important task that is carried out throughout VLSI design flow. Thank you.